J,
And I know that's like C,
C,
My advice is do what you want to do. Don't worry about it.
G,
You don't need my weekend. Maybe Paris. We have so many.
All right. Good evening and welcome to our LTU College of Architecture and Design lecture series. My name is Carl Dobman and I'm the Dean of the College of Architecture and Design. As you can see with the slide that we have up, we offer degrees in architecture, interiors, industrial design, transportation design, graphic design, game art, and urban design. I make a point of mentioning this list of degrees because it not only points to the incredible range in design, but it also helps to highlight the potential of our lecture series to engage all of these design approaches, methodologies, and mindsets. And this is true of our lecture tonight, and I see students from the various degrees represented here. And maybe not to date myself too much, but as a way to set up this notion of drawing, I'm from a generation of designers that was educated in analog methods in undergrad and completely digital methods in grad school. For the decade that followed, I witnessed anxious discussions in academia about the transformation from an analog curriculum to one that is digital, that of drawing by hand versus drawing with the computer. I was recently introduced to the increasingly fine distinction between digitization and digitalization, and there is a distinction between those two. Digitization is the movement of lines, say, as an example of drawing, lines on paper that are drawn by hand, to that of lines that are delineated by coordinates. These digital lines can then be used to do more, drive machines, output in different ways. Digitalization, again, that very fine distinction, is defined around areas of social or business models and allows for increased value within the process. With digitalization, it's not about producing the same output with different tools, but about fundamentally rethinking the opportunities available to us. And it was a couple of years ago that I overheard students talking about how they produced a drawing. One student told the other student that she drew it by hand. This caught my attention because they were looking at a Rhino model. I had to inquire. What she meant was that she drew or modeled what they were looking at on the screen without scripting, without programming, without parametrics. One click of the mouse equaled one operation. No loops, no algorithms, no functions. It's this type of fundamental digitalization, positive shift that was in my mind when I got Carl's book. He brought some too, and I brought mine. Computational Drawing, from foundational exercises to theories of representation. These types of changes are transforming not only the way that we work as designers, but it's also changing the work itself. And we're seeing it across all of our design disciplines. Carl's book and his work demonstrates new opportunities for the consideration of drawings. So it's my pleasure to introduce Carl Lostritto. Carl is a graduate program director and associate professor of architecture at the Rhode Island School of Design. With a group of interdisciplinary faculty, he recently initiated the university-wide computation, culture, and technology concentration. In academia and in his practice, he writes computer code, samples from history, designs tools, and adapts technology to augment human authorship in pursuit of architecture. Often this work manifests as drawings, and drawing in the broad sense of that word. His contributions to the field take the form of artistic exhibitions, essays, and professional collaborations on built and unbuilt work, and including his new book. Before RISD, he taught architecture and design at MIT, Boston Architectural College, Catholic University of America, and the University of Maryland. He studied a post-professional research program at MIT with a concentration in design and computation. He also earned his undergraduate degree from the University of Maryland. So please help me welcome Carl.
Thank you, Carl.
Welcome, Carl. It's nice to have you here.
It is really special when Carls meet. I was telling Jim there aren't as many Carls out there in the world, so it's the first thing that Carls say is like, "What do you feel about the C versus the K? Like, how loyal are you to one or the other?" And I'm agnostic on that. I like the C, but I've never been here before, but I have a kind of fondness for Lawrence Tech. There is a grad student in our MArch program now who represents you well. So I'm really happy to be here. So I'm titling this Casual Computing and Formal Drawing. And that, to me, is how we bring together computation and drawing. As you probably have already figured out, I'm interested in hybridizing them. But for me, that hybridization is fruitful not because computation and drawing are natural allies, but it's fruitful because they actually have significant friction and they push back on one another. So I'm going to give you two quotes that I think sort of set up this dichotomy well. The first one is a Picasso quote that you might have seen before. What good are computers? They can only give you answers. First of all, some people are surprised that Picasso was talking about computers. Picasso died in '73. And so this is, first of all, a good moment to sort of check in with computing culture. When we talk about the digital turn in architecture and design, we're often talking about the digital personal computer revolution, right? Like the Macintosh came in 1984, and design software became mainstream in like the mid-90s. You saw again in the 90s the like first paperless studio in Columbia. So in our disciplines, we often think about that era as where computation came into being, but that's not the case. Computation started in the 40s in earnest, and the first computer art was in the late 40s and 50s. And so the idea of the computer was present long before it was kind of mainstream in our everyday lives. So to me, that period of right when the computer existed and how people thought and considered it is really interesting. So Picasso is not wrong exactly, but to me, the idea that this idea of a computer, a thing that in its very definition computes something and solves something, how you push that to be not something that just gives you an answer but helps you ask questions is super fruitful, and drawing can help do that. An analogy I like to look at is the relationship between computers and chess culture. The moment where a computer started to systematically beat humans at chess was at first thought of as like the holy grail, but much more recently, computers that have been trained on neural nets to kind of learn chess on their own are starting to play in like surprising and unpredictable ways. And so there are now new questions about like the conventions of chess theory. So that to me is a really salient example, as like these machines that we program and that we can sort of understand or not understand what happens under the hood can still provoke us in different ways. On the other side, we have this sketch by Mervyn Levy that is sketching is the breath of art. And of course, yeah, it is weird. It's sketching, not drawing, but this is actually kind of important distinction here. It is the most refreshing of all the more impulsive forms of creative self-expression, and as such, it should be as free and happy as a song in the bath. So, you know, if the preconception is that the computers are stiff, drawing is like, you know, like a bird, right? It's like free and open, and it's just sort of loose, and it's like totally non-constraining. And I think it's actually very helpful to position drawing as exactly the opposite of that, right? Although the idea of resolution and fidelity and structure is open-ended in drawing, there are lots of ways that the material medium of paper pushes back and has really hard limits that are not the same kind of limits as computation. So I often use these Penplotters, and in this drawing that's being made here in this animation, the paper is a substrate in which ink bleeds through the paper and mixes with other ink. And so here it's green, right? You see this is a green drawing, but there's no green ink used in the production of this drawing. I think that's funny. It's like no animals were harmed in the making of this product. Like no green was used in the production of this green drawing. All of the most figural elements and the kind of character and quality of this drawing comes from the material relating to other material. If we were to do the opposite of digitization and do like a kind kind of stepping back and looking at the kind of digital roots of this thing, and we were to look at the kind of digital marks or the algorithms that would precede this material, it would look nothing like this drawing, even though the geometry was totally predictable. On the same hand, or on the same note, the paper of a drawing rips, right? So in the world of the Penplotter, where, well, I guess maybe think about the world of working in Adobe Illustrator, where you've got a black line, and then you've got 1,000 other black lines on it. The line is still black. It just looks black. You can't get more black than 0, 0, 0 black. But in the world of paper drawing, quantity and time, all of that have an implication, and at some point the material substrate isn't the kind of blank nothingness of a digital black or a digital white. It breaks and it catches and it snags the paper and rips. And sometimes I can catch it just at the moment like this, where it's gone past that breaking point, but it hasn't sort of catastrophically ripped and jammed the paper. A lot of my practice is sitting there watching a drawing that takes hours and hours to make, so I can catch it just at that moment. So I collect Penplotters. I kind of have to because I really want my students to be able to use them, and they're kind of awesome. And there are things that you can buy for super cheap on eBay. This little one is kind of quirky. I'm not really sure whoever would have bought like a laptop Penplotter. It cost in like the $5,000 to $6,000 range in the early 90s, which is unfathomable. Like when you account for inflation, that was like tons of money. They are, the reasons why I love them are the reasons why they became obsolete so fast, right? They're not reliable, right? Like each mark of a pen is like a little bit of the roll of the dice because it's a literal pen. It's not like file print at all. And I will show you in a minute the instructions that the Penplotters take. So this one is a photo that's part of an exhibit that, or we called it a happening, that I put on with a collaborator of mine, an architect artist in LA named Mike Nesbitt. And in this happening, we were joined by 2 improvisational dancers and choreographers named Jess Emanuel and Anya Catherine. And part of the reason why I'm showing this is that, you know, this interest in hybridization of drawing and computation is not just about technique, it's also a kind of about hybrid forms of authorship and hybrid cultures. So Mike Nesbitt, if you don't know his work, it's amazing and interesting, and in some ways a lot like mine, and in some ways not at all like mine. We're both architects by training who have practices that are a little bit strange and quirky and unconventional. Mike, who is also a former professional baseball player, is really in tune with his body in space. So he makes artwork that is fast and huge, and deals with like large bodily movements. He has a whole series that are called Swipe. He makes, you know, super large architectural scale things very fast, very viscerally, but also very procedurally, and is very in tune with the process being just as relevant as the outcome. So he and I met in LA, and we had this agreement that was basically on these sort of 3 premises. One is that we were each going to do our own thing in our own way, but we would be constantly passing work between one another. And that once we passed work to each other, we were free to just reappropriate it however we wanted. And that we were going to spend some time making work live instead of having work, you know, pinned up or exhibited in a gallery. And this is where the choreographers came in. They were interested in just sort of activating this weird event, which you'll see in a minute was on an LA rooftop. So I'm going to play this now, and then we'll talk a little bit more. I'm not from LA, but it's also kind of like this kind of thing could only happen in LA. So like, I also can like check off the bucket list, I did an LA thing. So there were a lot of things that were, sort of came out of this happening that were quite interesting. One is like the various time scales. So the Penplotter is a kind of very long process with very quick actions. And his kind of screen printing process is very deliberate bodily actions that involve him working with his collaborator. They have to sit there and say, like, okay, are we ready to do this now? Okay, go. But the output is much faster. So over the course of our 4-hour event, I made 4 drawings and he made 40 drawings. Mine were this size, his were this size. But exhibiting them together, I used cool colors, he used warm colors, and even in that event, we swapped a little bit, right? So he used one of mine. I was taking photos of his that were, my algorithm was referencing to produce the drawings. So the other aspect of this is that there was a kind of blurry line between analysis and content. So we were each in our processes doing some reflection on each other's work, and that reflection became kind of intertwined with the content itself. That's something I'm going to talk about a little bit later when we get to the scaffolding project. These are drawings that I did with a graduate assistant, a research assistant at RISD. And kind of in the same vein, this is aiming to make this hybrid condition that also questions the role of authorship. So in this setup, we took turns being the kind of algorithmic driver and the manual executor. So I would write algorithms that she would execute, and then she would write algorithms that I would execute. And these 2 examples are the former, but what we found most interesting were situations where I would give the algorithmic instructions, but they were so constrained and open-ended that this is actually 2 results of the exact same algorithm. So basically, I was giving her dots, and she had a micron, and my instructions were connect all of the dots with as few lines as possible, but absolutely can a line never cross another line. And the dots that I gave her were just projections of an interior cube in perspective. And of course, that's a little bit like the traveling salesman problem, an interestingly famous computer science algorithm to look up that kind of deals with this question of how do you optimize something that's kind of borderline impossible to optimize because testing all the possibilities is kind of quantitatively impossible to do. So this, these are beautiful in person because she also took sort of notes as she was going. So this is disrupting the kind of normal way we see like the person who makes the algorithm is sort of like the master. Like it also used to be a kind of wildly inappropriate and problematic trope in early computer science. They would call them master-slave algorithms. So there's a whole bunch of problematic sort of literature and culture around computer science that kind of overly glorifies the like master programmer. And so our aim was to disrupt this. And I would say if we were to assign authorship here, it way more should go to her than I, because I was sort of setting things up. But every key decision here, everything that affects how you read the drawing was hers. OK, so we're back to the world of Penplotters now. Some of them have an X and a Y axis, kind of like a laser cutter moves. But the important thing that you need to know is that the ones that were made in kind of the late 70s up until like 1992 use this thing called the Hewlett-Packard graphic language, which is HPGL. It's an open specification. HP was trying to compete with PostScript. And they lost, and so this is now just a kind of legacy thing. It's super simple. So this is also like you would see if you're giving machine tool paths to a CNC. It looks a little bit like gibberish, but I can explain it to you totally. It's 2 Commands are 2 letters, so SP stands for select pen, PD stands for pen down, PU stands for pen up, and then the numbers that follow are the inputs to those kind of like functions. So SP1 is select pen 1, PU negative 2709.13 comma negative 649 is move the pen with the pen up off the paper to that point, and then pen down to those other coordinates is with the pen down, move to that other coordinate. So now you know HPGL, and so if you want to control a Penplotter, you just have to send these commands. And the Penplotters being of that vintage, they use a serial port, which is also out of date. But serial ports are awesome because there's no compression. You could sit there and type on a keyboard and send things through the serial port. So that means that my fancy, absurdly fancy laptop can connect with like a $5 USB to serial adapter, and you can type in the terminal, and it will just sort of pretty much out of the box make drawings. So you can kind of do it as a kind of terminally Etch-a-Sketch if you want to. And so I do programming in sometimes Python in Rhino script, sometimes standalone Python. I've made a Twitter bot that you can control a Penplotter. The HPGL is so basic that you could do almost anything you want as long as you can generate that script. And of course, I'm not actually typing that in because that's kind of like Etch-a-Sketch model. Like I know artists do Etch-a-Sketch art, but like it's amazing. It would be so tedious, right? So I write scripts that make that code that then make the drawings. Sometimes what's really exciting about that is that the first time I ever see the drawing is when the plotter is making it. So there are ways that you can work around that and generate like a pixel-based image or put some stuff in a Rhino model to kind of preview it. But the drawing really doesn't exist until it's a drawing. So this drawing, which is on the cover of my book, obviously has a special place in my heart because I had to pick a favorite. Like it's not something that people like to do, but when a publisher asks you like, okay, what's going to be the cover? You apparently have to answer. And so this one, I thought is kind of special because you can't help but see some depth here. So this is how I this is how I think architects and designers think differently than other artists, right? Like we are really invested in ways of shifting and being in between 2D and 3D. The other interesting thing is to refute the Picasso quote, this drawing happened by accident. If I'll zoom in here, as you can see, these are like sort of spirally lines that are made up of different color pen segments. And so if you've done any programming before, this will make sense to you. Maybe it will make sense to you even if not. But it's like a loop inside of a loop. And so the inside loop is like doing this sort of circle, right? And then the outside loop sort of says, okay, do a set of those circles. And so the outside loop governs that some parameters that makes each subsequent loop look at the previous loops. And so there's like a bunch of code for the inside one that's all indented because it's in Python. And then the outer loop is here. And then there's a little line that generates the SP code, the like select pen to change. And my intention was that each loop would be a different color. So the select pen was supposed to happen in the outer loop. But I was lazy and there was a typo and I forgot to de-indent it. So then the select pen was in the inner loop, which meant that every little segment was the switch of a different color pen. So that also unfortunately meant that instead of this drawing taking like 3 hours to make, it took like 30 hours to make because every segment it goes and it like does this little dance to take the next pen and does the next little segment. And it's not just like a color switch. Because it's getting a new pen each time, there's an accentuated change in that little like dollop of ink when the pen goes down for the first time. After you've been drawing for a pen for a while, the ink doesn't pool up in the felt tip, but if you're constantly letting them rest, every time you do pen down, it it has a little mark. So these marks are now, you can tell by looking at this drawing the direction that the algorithm was moving, because the down leaves a mark at the start of the segment, but the up does not. And then, of course, there's that red blemish up there, which is because there was so much back and forth going and switching that eventually the paper buckled a little bit, which is a common thing. And so it turns out that the up versus down is only like 2 millimeters of difference, right? So as the paper is moving back and forth and the pen is moving and the paper buckles a little bit, forces can conspire, and then like when the pen is up, it just makes a little mark there. And if you were doing an architectural drawing, right, imagine you're doing a drawing set and this is how you do your output. Because when these were in offices, it was at that moment also where there wasn't enough memory to rasterize large format drawings. So there was a time when you could do file print, but you couldn't do it large, because even your vector-based output in your plotters, there's probably like 250 megabytes in your large format plotter. It does its rasterization at the time that you do file print, and it converts the lines to little droplets of ink. That requires some bits of memory that didn't exist in the world, basically. So this was the way you output large drawing sets. So anyway, imagine you're doing a drawing set, you're about to send it out to a client or something, and then there's this horrible error. You can't, it's like unusable. So it's like horrors if you're doing output of drawings, but kind of curious and interesting if you're just making speculative, abstract architectural art. Okay, so I cultivate these really simple algorithms. So on that same premise that I'm interested in kind of looking at ways we trigger depth, Python is an object-oriented programming language, which means that you can write things procedurally, but you can also define the behaviors of things. So this is me defining the behavior of a line that just sort of spirals around. So I'm setting parameters like when does it steer? And how does it tend to avoid itself? So I'm really designing the characteristics of the line rather than the line itself. And again, like look at how pixelated this is, right? You could tell this is for me to sort of work out the algorithm, but this is the thing. This is the thing that I care about. I'm interested in that you're seeing this as a one-point perspective, which of course it is not. It's just geometry that happens to converge at a point. I'm interested in that rich blackness where it's not just that you can't see every individual line, but there's so much black that the paper itself is like sopping wet and changes its characteristics. I tell everyone this. I have a pathology where when it's an algorithm, I can't show just one. So you're seeing two of a lot of things, because I think it's like sacrilegious to write an algorithm and then just show one. This is a really simple algorithm that also confronts the kind of digital overlappiness. Digital overlappiness is my term for like, you can, in SketchUp or Rhino, you can just collide things and it's just like whatever, which is not how material works. And so, of course, you've got like BIM solutions to that where like collision awareness is a thing. But I was interested at the algorithmic level, what would it mean to define a line kind of as an object that understood the line to be like a little fence. So as it spun around and traveled like it had a car with a steering wheel, it would travel so that it avoided itself, but it was also a dashed line. So as it traveled, there were also little gaps. So if it spun and got out of control, it could eventually find its way out. And over time, the line, the spaces would become larger, but the kind of the scale would also become smaller, so that it would prevent it from getting too stuck. Excuse me. This is one of the outputs and another. I like this one better than the other one because there is this moment where it almost breaks down in the corner. It was stuck there for so long that the paper was just about to rip. So I have to take a drink of water, so imagine what the algorithm is here. I like doing this, by the way. I'm really into publishing the algorithms because I think they're interesting, but some artists have this thing where it's like, it's my algorithm. It's like my property, like that's my thing, and I would never share it because it's mine and I made it, and if I shared it, you would steal it and make art that was too much like mine. So there are some computational artists where I stare at the work for hours, and I'm like, what happened there? Then occasionally I get to find out because I find it's published somewhere, or I know somebody who turns out they know, and the answer is always way simpler than you think. So anyway, this one is actually not that simple. It's get this. I have to read it because I mess it up so often. This is a 3D simulation that plays out forces that make a simulated drawing, which is translated to machine code and then plotted. So it's actually more complicated than that. That's like the clean version. But there's a digital simulation of a double pendulum, so a thing with weights spinning and another thing with weights spinning, which you can make physically, but it's super expensive and hard to calibrate. So I just made it digitally and then pen plotted the output. So this is sort of like the digitalization of something that would really love to be analog, but it was only kind of efficient and possible to do because I could do it quickly on a whim digitally. Okay, so this is a special little artifact. So this is, okay, I'm gonna back up a little bit. In my apartment building, one of my really nice neighbors moved out and he forgot to cancel his New York Times subscription. So for about 4 weeks, I was getting the Sunday New York Times, which is awesome. Very expensive, but awesome. So I'm reading this Times magazine this day about a year and a half ago, and there's this puzzle that's like these arrow puzzles, arrows and targets. And so the way the puzzle works is that they provide rows and columns with numbers, and then there's a few targets, and then you put in arrows, and every target gets pointed to by an arrow, but only by one arrow, and then the rows and columns describe how many arrows are in each square. So I played this, that's kind of fun. You can see I didn't take it seriously. I was doing the mini crossword, and I didn't want to mess up because I only had a pen, and it was glossy paper because it was the Times magazine. And so the answer was NyQuil, but I had to write out the 2 different ways I thought you might spell NyQuil to see which one looked right. So anyway, I wasn't taking it. This is like proof that this is like a genuine, real life thing I found and then turned into a whole other thing. So I thought, so again, think about to this Picasso quote that like computers only give you answers. I thought, well, this is an interesting kind of puzzle. It's a little bit like a Sudoku, right, where you know that a computer could solve it instantly. And so there's not like mystery to it, but like the process of solving it was weirdly spatial. I had to sort of put X's in the box because I knew there were sort of buffers that there couldn't be arrows. So like, this is odd, like a spatial diagram in a way. And I was like, well, it was Sunday, and I think it must have been Sunday in a summer, because if it was Sunday in the fall, I would have been teaching on Monday and I wouldn't have time to do this. So I'm like, well, let me write a little program that just solves these puzzles. Because my hypothesis was that a bigger version of this could be really beautiful and really interesting, and that there might be puzzles that would take years to solve, but if I could figure out computationally what the rules were, I could do the reverse. Instead of solving the puzzles, which of course I just had this one, solving is irrelevant. Like I've already solved it. This is the right answer. I could have just moved on, but I thought the idea, like I thought there could be something to producing the thing that would solve it. I could use it generatively. So I do it. I actually took more time to get it to output something nicely, right? So like just the spacing and the graphics and monospaced fonts and what should the arrows look like. I spent like 10 times as much time on that, on the actual programming of it, because it's quite straightforward. So then I made them really, really big and really, really bigger. And then I started to animate, like decide, well, what's more interesting, to do the input of the targets or inputs of the numbers. I did different gradient things. I think I might have an animation. No animations here. But then it's again, the Penplotter is really for me what makes it all something different and interesting, where all of a sudden the resolution of the arrows is so much that the arrow direction doesn't matter anymore. But the color of the Penplotter